differ by pi, for example, then they precisely cancel each other out. And if they're just random phases, they sort of combine in some way, partly adding up in some way, partly cancelling. So we want to see, in a sense, do we expect that these two things, when we add these up, and remember we have to integrate over all paths, so we're adding up all paths, so we're certainly adding this one and this one, amongst others. How do they combine with each other? So that's to do with the phase difference here. So what we want to do is imagine for small eta, we sort of expand this, exactly like I've been saying over here. So this thing here, we can write, so it's e to the I over h bar s of q. And then we get the linear term, which in fact we've written, integral dt Okay, so we get some exponential or something like that. And we look at the phase difference between these. So the difference between the two phases up here so we just subtract that phase from this one up here. So obviously, the first terms, the action evaluating q, cancel out. So we get I over h bar. So the same factor here with the other Lagrange equation. Okay, so that's the linear term, and then there's terms that involve eta squared and higher powers of eta in there. Okay, so when we sum over paths, typically, will this phase difference, will this be a big number or a small number? That's basically what we want to ask. And so precisely what I want to say is, if we take eta then to be some small deviation, so think of some path like that, and some other path q plus eta, that's very close to that, then we have to be slightly careful what we mean by close. So do we mean close in the sense classically? So if I do some classical experiment, then of course, if you see a particle moving, then of course there's some typical error in how closely you can measure its path, and there's some notion of how close two different paths would have to be before you couldn't really tell the difference between them. Now there's also another scale, which is why I've kept the h bar in here, and that's, in a sense, how close the paths are if you think down at the quantum scale. So, of course, the idea is that some problems really are quantum mechanical. So if I think of an electron going around a proton, for example, in an atom, then we think that that's quantum mechanical because the scale of the path is something that we can relate to the scale in quantum mechanics. Whereas if you think of course, usual thing people talk billiard balls, for example, then the quantum scale there is absolutely minute compared to the scale of the experiment you're doing. So there you would expect some classical notion to appear. So what we have to do is we want to say, if we think of eta as being small classically, but it can still be large quantum mechanically, so somehow this thing over h bar could still be a huge number, because in classically you're thinking of things happening where the scales are much larger than the sort of scale you think of as being set by quantum mechanics. So when summing over paths where eta is small, classically, then phases in the complex plane. So the phase I get here corresponds to my Q, and then another one, a huge would be much, much greater than. So essentially that thing is random, and so typically they all come in with just completely random. All the points will just fill up all the points on this unit circle. I mean, so of the nearby paths, term here completely vanishes, and eta vanishes. And so what I could have so when we take the classical path, then so that gives you something of order eta squared, because precisely the terms that were linear in eta are the ones that vanish when we ask for the Euler-Lagrange equation to be satisfied. So this is precisely this down here, and for the classical path, that is always 0. That's the condition for this classical path. So the phase difference then is something of order eta squared over h bar. And again, of course, there's some integral of some stuff in here, but just loosely, let's say order eta squared over h bar. And this can still be small. So and so if that's small, then these paths add in phase. So basically what we have now is this idea some phase corresponding to the classical path there, and then the nearby ones don't differ by very much, though they're all around, say, something like that. And typically then when you add these up, you get a large contribution. So Okay, so for different etas that are small in the sense classically small, then we get these contributions like that. So that's the idea. And roughly speaking, then these things add up. So a little bit of cancellation, of course, but roughly they all add up. So this means the dominant contribution then to the path integral is from paths close to the classical one. Okay, so somehow, typically you're getting cancellations, but in a special case where you're near this classical path, then things add up together, simply because the phase differences are smaller, because when you expand the action, the first term in the expansion vanishes for that path. Okay, so perhaps we should ask then, are there some questions at this point? Okay. Okay, so what we'll do next then is we'll see some examples of how we calculate this path integral here. So for an arbitrary action, or arbitrary Lagrangian, then we can't calculate this exactly, but what we'll see is in some cases we can calculate this. So there are special cases, and it's essentially when the Lagrangian or the action is quadratic in Q and Q dot. And the reason we can do these cases, of course, is because all we're really doing, if we go back to this definition here, we're doing various integrals over the Q's that appear in here. And if we have exponential of something quadratic, that's a Gaussian integration, and we can do these integrals exactly. So basically, these are just simple examples then. Okay, so the idea here is basically going from what we said. One way to approach this is, rather than just writing the sum over all paths, pick out the classical path and then sum over all variations from the classical path. So the idea is replace Okay, so obviously if I sum over all paths, I can sum over all eta, adding on to the classical paths. It's just a change of variables. And it's linear, there's no factors coming in, so there's no change in integration measure or anything like that. So what does the path integral become then? So what we're doing is putting Q to be the classical path plus eta. So